So I won't do the entire curve, I'll do curve back. So what did he tell us? So he said that so there is every point x of the Rand space. With a localization marker G, and that organizes itself as sheet map between sheets of categories in the Rand space. And so when he regards KL as sheet of the Rand space, it goes down the line. And so back from the line again. So it's a constant sheet of categories. That's valid every point is that. So this is not on the line. And so then he said that his notation for log is we can take the global sections of that. Log count sub one. You go to the tensor, we will run, and then we integrate out the identity tensor the lower run the lower to and so this is the function that's under.
They want spongy.
And this is the function that appears like left vertical upper arrow. Okay, so let me just so yes, the main thing that this guy is uniform with the global function. Earlier today, so that was the purpose to mix up. Now, so we say a few more things about this ds that appear. So now there's a function ds from KL on the line to that on the line, and that is laxity result. Now I'll draw a false assertion, which is exactly May's theorem, but take the false one. So I'll do KL1 and do this localization go to be on 1G, and then we'll take coefficients to that. And so this log was obtained from a local global function, and then it followed just between two global functions, so you can think this whole thing is obtained from a local to global function. And now, like this ds, which is local to global function, lax until will go to that. Okay, they said wrong. It's going to be very, and then they take it in the book. So let me just split it. This is two. It's a log one.
I think I'm going to explain what we want to
Yeah.
show. Later.
This is just an efficiency. And the identity, so I'm now writing local to global functions. So this was log underlined. So this is ds underlined. This identity. So false assertion with this diagram commutes. Why is it false? Because this guy is uniform, and this is only lax unit.
So that's what I'm going to say.
Yeah, okay.
Yeah, okay. For yours. Okay, let me continue. So
I just want to draw something.
yeah.
Oh, it's wrong.
So now let me start to talk about the proof of this main theorem. So as Stanley said, so I will produce something that is not commute, and I will tell you how to fix it. So the thing that is not commute, I will use my notation. So I will draw this underline, which is a shape of category. So we apply this loc underline to this D of bound G, conserve with this vec underline. So this is a local global function in terms of shape of categories. And here, so we will just apply this coef vec for the first vector. First factor. So therefore, it just goes to vec underline. So it's if you want, I should write conserve with ID. So I can do this. And here, what I can do is I can do this ds underline, so which goes also to vec underline. And here I will draw this. But unfortunately, so this does not compute. So later I will construct a natural transformation between them. So but before that, let me explain why on the field we want to compare these things. Why these things can be related. So this semi-infinite cohomology, this trivial circular reduction, as I told you, so it behaves like taking cohomology for this loop n in a mixed way. And Gruber told you it has some, in some sense, it behaves like some Hamiltonian reduction. And this coef vec, it pull back to bar n and do this direct image. So I thought Sam also told you it behaves like some global Hamiltonian reduction. So you can view this left vertical thing as saying we have some local category KOG, we have some version of local Hamiltonian reduction for this n to go to vec. The right vertical is like we have some global category D of bound G, we have some global Hamiltonian reduction, and you may expect there's some local to global principle telling you that the integration of the local reductions would produce the global reduction. So you might hope or wish something like that may happen, that this function is really just equal to that function under this loc. But as Stanley said, this is too good to be true. So namely, so it does not commute on the object that we have. Namely, so let's consider just vec. And see who goes to who. So we view vec as a, say, factorial algebra on this KOG, for instance, but you can also just put it just as a point. So let's see what's the image of this vec under the functional loc. So Sam told us it goes to the stiff. Here we are in a constant family. Maybe you want to say a stiff tensor with the constant section inside this vector, which I denote by this one underline. And if you get confused, just ignore this. So it's stiff everywhere. Stiff means differential operators on bound G. And now you do some coef. It's still something constant. So you may not know what's the image. That's fine. Neither. It's something constant along vec. So, but if you do the left vertical thing, so it's actually calculate this z. This is a second. Yes.
DS vec.
What?
DS.
Yes. DS vec. Think about what's the notation. So which is z. So here we really view this z as a fractional algebra on this vec. Fractional algebra on run. It's not something constant. So like the fiber at x is one piece of z. The fiber at x disjointed with y is two pieces of z. So it's non-constant. So therefore, these two things really can never be equal because the left hand side is not constant, the right hand side is constant. Another way to say is this is like this right vertical functor is definitely unital. So this thing is unital, but this thing is only next unital. And you can never expect a right next unital functor, local global functor, to to be equivalent to a strictly unit one. So there's no way to believe that. But so in next talk, he told us that there's a universal way to produce a unit of fraction functor or unit of local global functor out of a next unit of global functor. So namely, let me remind you.
Just to repeat my comment, that one of these things is global, like this coefficient of diff, knows about the changes to the curve and things, and the thing on the left is completely local. So again, this is the issue of global versus global.
Yes.
It just has to be corrected, not for like category reasons, but just for like at all the type of thing in advanced reasons.
Yeah, also according to your definition, this functor is also a local global functor.
Yeah.
It's something from Shiba around something constant.
No. It's 8.2. Let's move on.
Well, okay, so
How do we see that it's not constant? This is Z.
as I said, D is a non-trivial fraction algebra. Its fiber at a point is dx. Fiber at x different y is dx times dy. So, and these two things are not the same. Unless D is true, but we know it's not. Because we have a critical level of the results. Okay, so so we are saying, so let me remind you, if you have a local global function from C to in this location, C below times something, so I will just write D tensor with this big vector. So here this P is really just a unit category. So this is my replacement for next unit of local to global. There's a first way to produce a unit one out of it. So namely, so he denoted this by this notation. So S subscript or in fact, or I'm so lazy, I will just write F fix. That means you fix the next unit of C. So this is given by the following. So if you start with a point on the right, so you consider the Cx, you can invert the vacuum to go to this C run X. So this given by the unit structure of C, and you just apply your F to this section, you will get D tensor with D mod on this run X, and then you do this integration, you go back to something D, and this is the new functor, so obtained by this procedure, which is the fiber of your Fx at X. So in other words, you define this functor as some combination, and you assemble them so to get a functor with the shape of categories, which is again a local global functor. And what Nick told us is you start from some F. There's a universal way to produce a unit one, which I know by this F6. And the structural construction. So therefore, when we look back at this picture, so this natural transformation, I haven't discussed it, but as long as we have such a natural transformation, we can factor through it through some other natural transformation. Namely, so this natural transformation tells you this ds maps to the combination of log followed by this coef vec. I'm using some shorthand, you know what I mean? So the source is next unital, the target is unital, but the universal property, it has to factor through this ds fixed. So there exists such a thing, and now let me write this as a construction, which I will explain later. This is some key construction, and from this key construction, so we obtain a natural transformation, which is from ds fixed to this combination we want. So we obtain that. And now let me rewrite this main theorem in the other way, and I will give it as an exercise for you to see that they are the same. What? Yes. So fixed means exactly vacuum and then integration. And just two nice. So this is main theorem one. So which just says that the natural transformation you obtain from the construction is actually an equivalence. It's an equivalence between unital local to global functors from KL to back. That's main theorem prime. And let's point out this and to convince yourself that main theorem one is equivalent to main theorem prime. So it's really just follow from the definition of this fix, because fix is first in that vacuum and apply your function and do the this integration. And you may compare these things by translate between two languages of local to global functors, and leave it to you to convince yourself that these two things are equivalent. So any questions so far? Okay, so if I run out of time, I will treat the proof of this main theorem as a black box. So instead, so what I really want to do is I want to explain how to obtain this construction and how to obtain this natural transformation and some other things related to it. So there are several other results which is also of the same thing. So I will use this board to do this.
Is this like fixing construction universal in some way?
Yes, it's the left adjoint. So in other words, if you have some next unital thing mapped to a unital thing, so it always factors through this.
Stated as such is mixed star.
What?
Stated as such is in mixed star.
Yes. Also the view of there. Okay, so I think it's section 4. So I will do something very similar to that, and I will state another result, which will be used, maybe used in future lectures. So let me remind you some construct the following diagram. So just by Cooper, so we consider this graph of R group. We can also make a factorization. So view it as a uniform shape of pathways. So here the unital structure is given just by trivial representations. It's easy to imagine trivial representation gives you a unital structure. And here there's this in function. So which goes to this KL. And this function is a unital function because it sends the trivial here to back here. And that the unital function algebras. And we have already enough time to define this log function. So I will not repeat it. And in some scope, he explained another function which now we denote by this log Q-co. So it lets me Q-co of 1G. So that's the meaning of the name. But we also view that as a local to global function. Therefore, I write it in this way, which is what I prefer. And this is in function ID. So this is in. So Sam explained that this diagram commutes. And if you forget how to prove it, so let's do a sanity check on this particular object. This tree is a trivial representation. There's no Q-co, it's just given by some pullback. So therefore, it's a trivial representation for the structure shift when it comes this constant section. And now you do this induction, so you will arrive at this piece of this constancy, and we indeed go back listen to this piece. So that was explained in some talk. So far so good. So this is really a complete Now let's play with it. So this induction is never joined to the forgettable function. So therefore, we can try to do the following. So you just pass to write the join and obtain this diagram. However, this cannot be commuted. So in general, so if you pass to a joint along some direction, what you get is a natural transformation. So I will just tell you the direction of it. Do not bother to look at it yourself. This is so-called Bayesian natural transformation. So we obtain a natural transformation like that. So you might hope it to be invertible, but not. But exactly the same reason this diagram fails to be commute. So namely, so let's look at the nature of these functions. So we start from something called KL to something on this Q cobalt G, some local to the global function. And let's look at what's happening to the unit. So I claim from this arc this unit. So because you send this back to something constant, which is D fox 1, and whatever the strategical thing is, it's still something constant. So therefore, this function is unit. So, however, the other function cannot be unit. It's only next unit. So it's next unit because it's the combination of ordinary with log Q code. Log Q code is strictly unit. As we explained before, this forgive function is the right joint, and therefore it's right next unit. To see it's not strictly unit, we just look at the image of this forgiven function. And this guy is not sent to trivial module, it's sent to that we use as something and it's only a map between them, which is not an either. So that's the reason why this net vertical function is not related. It's only next to the and therefore we cannot expect them to commute. However, so what Nick told us is that now you have a natural formation from next unit of thing to unit of thing. So therefore you can try to fix it. So you consider this combination. So this arc which is open followed by pupil. So this natural formation actually induce a natural transformation from this tip to the other arc, which is log followed by this opulence. I will use notation in what I mean. You obtain such a natural transformation, and then you write a serum, then you have serum 2. So this is an acid. So it's of the same flavor as the main theorem we discussed. So we first construct some natural transformation from next unit of thing to strictly unit of thing, and then we say factor through the fix, and we claim it induces an impedance between the fixed. So far the thing we have done, you can say it's in some sense formal, but the proof of some tool is not formal. You need to do some really interesting calculation, and we don't have time for that. So if you are interested, you should look at Nick's thesis. So maybe published in 2021, 10 years after this graduation. Yeah, so you will find a very beautiful proof of these things. And also, if you want, I can explain to you what the main idea behind this, maybe after this break. Anyway, so this is the compatibility of log and the forgive function. So I'm stated because it looks similar to that, and maybe later we will use this in log.
Interesting interjection, let's make a pause for a second. Here's some substantial happen. This factor define localization function and what we can describe is what the proposal for the forgettable function for the computer sheets. And kind of naively forget from elusive representation of this data plus G, and kind of naively go back to what we call sample evaluation. Right? But that doesn't work. But we will not fix it. We will fix it. two more things of this sort will happen now.
Okay, so let's come to another example which will be used in the construction of the natural formation in the main theorem. So it's called knock and pullback. So recall this coef back is given by pullback from bond G to bond N and do this direct image. So to understand compatibility between knock and coef back, we need to first understand compatibility between knock and pullback. So now let's do some general thing. So suppose you have H1 maps to act on Y1, and you have H2 act on Y2, and suppose you have a homomorphism between H1 and H2 and a map between Y1 and Y2 intertwining the actions, and we call this P. So using the first action, you can construct a localization function as in some talks, which is H mod maps to D mod on Y1, H1. And here you have H2 mod maps to D mod on Y2. And let's study the pullback factor from Y2 to Y1. So this is the upper shrink. So this is really knock. And this is knock. And you might want to try to describe this pullback. There are something purely in terms of the algebra. And the only way you can make sense of it is try to say this diagram commute. Here you use the restriction factor. So you have a homomorphism from H1 to H2, you can restrict to produce a module for H2. So unfortunately, this diagram does not commute. So instead, you only have a natural transformation of this direction. And I leave this as an exercise for you. So Sam told you how to define this localization using pull push, and now some correspondence, you can draw some diagram and play with it. So you can prove that. Or more classically, so you can just write down the homomorphism between the Lie algebra and time spaces and very explicitly verify this. So I leave this as an exercise to you. Not too hard. So now we apply this to the following setting. So instead of considering H1 mod and H2 mod, we'll consider the corresponding loop version. And instead of considering this loop, we'll consider covariant version. So I think it's easy to believe. So you have the following natural transformation.
There's the best.
Yes. I'm writing with some London order here. So in this direction. And again, so you can even give this talk. So this diagram cannot compute because one of the arc is unital, the other is not unital. So namely, this arc is strictly unital. So but this arc is only max unital. Because unit here is vacuum for H2. So its image is definitely not vacuum for H1. So there's only a vacuum image.
I know exactly for what you.
No, arbitrary.
Not sure. Doesn't need to be redacted. But you need to be careful about levels, which we work with. So we have such a natural transformation, and then so I want to take this. I'm going to use that. So just like before, so we obtain the following thing. This is log H1, and you can fix it, which means insert the vacuum and apply the function and then doing integration. So this would maps to the computation of log H2 followed by P upper shoot. And claim, so I think this is term C. So this is an iso. Just like what we did before. But now I claim this follows formally from term 2. So it's actually an easy exercise And to prove it, you only need to draw some thing, some cube. So I leave it to you. I will just tell you the main idea. So the forgetful function from D modules to quasi-Coulomb shift is conservative. So therefore, to verify some natural transformation is immutable, it's enough to forget to quasi-Coulomb shifts. So here we want to compare some two things on D modules of bond H1. You can forget Q curve on bond H1 and using the previous result, try to play this, try to do some diagram tracing and try to play this, try to prove this. If you do this, you will realize you need to prove some very basic thing about this fix. You need to show it's compatible with computations. So I will write this as a hint. So I will say this FG fix. So F maybe so if C is unital and also if phi is any global function. So it's not any function between constant things. And this hint is some good exercise for you. So it's really just a manual definition, and you will see how it works. So I'm just saying this construction is compatible with computations, as long as these things are well defined. Okay, so this is compatibility between lock and pullback. Any questions so far? Which one?
Like the left where you say, like, is this like, so this composition is uniformly then?
Which combination?
Well, the uniform composition.
Oh, okay, you want to ask which one is uniform?
Well, like, I'm confused by like the right arrow seems to kind of like if you did it.
Yes, but here this is a constant shape of categories. And being unital this means some constant. We'll have one constant this. If you look at the definition of unital categories. Or you can just look at this completion and try to see what happens. Okay, so this is compatibility to lock and pull back. And what's next? So we should do push forward. So here you can also do a similar story. So instead of doing that, I will just cheat using duality. So here we have such a diagram. So I claim all the functors or all the categories in this diagram are self-dual. So this is actually a fake claim, but let's believe this, pretend it to be true. And moreover, so we can describe all the dual functors. So I will first draw the fake thing, and I will tell you in what sense it's true. So so far we don't know what's the dual functor for rest. So let me just write that as rest dual, whatever. So later I will show you what's that. And what's the dual functor for lock? A question to all this.
Global sections.
Yes, some told you it's global sections, but only for quasi-compact things. So here we know that bond G or bond H is not quasi-compact, but it's not a big deal. So first you can restrict to quasi-compact opens and do this story to prove everything. Also later we will only apply this to bond N, which happen to be quasi-compact. So no worries for that. So I will just write this guy. So this is gamma. So you forget the D-module structure and picking global sections. And what's the dual for upper shrink? So it's the Durham push forward functor, which we denoted by Pinot star. Two. So it's back. And here is gamma. And what's the direction for this natural transformation?
And just to remind, this gamma is little sections on bond H with level pressure.
Yes, you are correct. Yeah, I think you're correct.
Direction is the same.
That's. So because later I will pass through good. So okay, so what's the natural formation? So I will not bother you, so I will tell you the correct direction is like that. So it's like passing to duality as covariant at the level of two morphisms. This is something else to look at this. So anyway, so we have this, but it's something about log, not something about it's something about gamma, not something about log. To get something about log, we want to pass to some adjoint of this. And indeed, we know log is never adjoint to gamma, at least for quasi-compact things. So we can just pass to never adjoint to get rid of these functors. And now this natural transformation, it will change direction. So I will not bother you. So this direction goes this way. So what I said is you can go from this to this by using duality plus picture. So you get this compatibility. And I can imagine you know what I'm going to say next. So we have a natural formation between two local to global functors, and one of them is next unital, the other is unital, and it's not an equivalence. So but it induces a natural formation between the fixed guy to the unital guy, and it is an equivalence. But under some condition, and to state it, so let me first tell you what's this assumption. So if the map from H1 to H2 is surjective, and the kernel is equal to some nilpotent group N, so this condition, so it's here for two reasons. Let me first tell you the naive reason. So you want the fiber for P to be quasi-compact so that you can define direct image. So that's why you need bound N rather than something else. So the other reason will be explained when we explain the proof of this sum 4. So if this happens, so I will tell you what's this residue. And it's really semi-infinite homology for this LV. So also known as PRST function. So and in this case, so we know what is obtained via the fix. So we first apply this PRST and do this log H2. We fix it. It maps to log H1 followed by P lower star. And the claim is this is an iso. So this is theorem 4. But unfortunately, you cannot deduce theorem 4 from theorem 2. So because it's the other direction, you have to do something more. And now I'm going to explain to you what's the thing behind this theorem 4. But before that, any question?
Is there
N should be nilpotent. And I said the first reason for this condition is you want the fiber of P to be quasi-compact, so that this P lower star is really something well defined. But this is not the series reason. The series reason will be explained soon. So, but any questions for these statements?
So did you explain the dual of restriction is ERST instead of what?
That's a kind of I don't want to explain. So so you have to unwind the definition of the self-duality on this KL. So the self-duality on this KL as explained by Gerber is given by some semi-infinite homology. And if you really do it carefully, you will realize the dual function is given by that. Or So if you want, you can rewrite everything in terms of int code on some stacks. And this restriction is given by shrink pullback. This dual functor is given by direct image. And this direct image behaves like some fixture or some hybrid between homology and homology, which is BRST. Which one? Yes, so there are two. The first fake thing is look does not have a continuous write good. So because sponge edge might not be quasi-compact. The second fake thing is D of sponge is not self-due in the naive way. The did one does not work because it's not compact. But these two failures, they cancel each other. And when you first pass to duality, then pass to fake shape A, so you don't see this these fake things. Just believe in me. If you don't believe it, just restrict to some quasi-compact open, you will see it works. Okay, so I should explain the proof of sum 4, but let me first tell you that sum 3 plus sum 4 plus some twist, so which has to do with this Whittaker character would imply this main server. So because after all, this for back is given by a pull followed by push. And we know how to compare localization with pull, and we also know how to compare localization with push. So you can just combine two diagrams together, and using the fact that this fix is compatible with this compilation in a good way to obtain the main server. So this is something pure formal. And do people believe that? Okay, so now I'm supposed to explain the proof of sum 4. So do we still have time?
Yes, so let me just, I have a. So you were also supposed to do repetition beyond that, but you don't need to do it. Because yeah.
Let me do it in 2 minutes.
Perfect, but please do explain it here and for.
Okay, sum 4 is something very, very important. So let me explain.
I said, like, in some cases, this fixed time, as like, most classical descriptions of like, calculation homology,
It's inaudible. Yes.
Yes.
I explained at the very beginning. So first half of this lecture. So remember, I ended with an exercise, and you can write it as user function homology.
Yeah, but I guess sometimes there's these things.
You also have that.
You do.
You do.
So it's technically.
Similar description, like the next unit of instance, vacuum to some function output.
You say.
You don't do function movie or that function output. But you may need to relative to continue to this.
Wait, but it's that.
Yeah.
Right, good, yeah.
Okay, let me explain. So what's the thing behind this this sum 4? And for simplicity, let's assume this H2 to be trivial. So if you want, you can say, so we just look at a single H2 bundle and calculate the fiber at this bundle. So we can do this. So therefore, let's just go to vect. And here, this is just unit KON. And this is log n. And this is D of bar n. And vect. And this is just the global section. The round global section on this bar n. And this is to vect. This unit. So we want to understand, so this diagram and to show that after we apply this fixed operation, so it becomes inverting. And to prove this, it's enough to look at the generators. So to verify something commute, you only need to verify it on generators. And let me explain, so what's happening on generators. So first, let me write this as in the form we want. So we want to show if you start from some KLN X, you can first invert the vacuum to go to this KLN run X, and you apply this BRST to go to D of run X. And you here you do this log factor to D of N
Look X, look X.
no X, and you do this run homology to vect, and this is run X. We want to show this diagram commutes, and I'm going to calculate it on generators. I will do this calculation for vacuum. So let's start from vacuum on here. So here we are using another feature of this N. So namely representations of a nilpotent group is generated by the trivial representation. So therefore rep arc N is generated by trivial representation, and therefore KLN is generated by its vacuum representation. So it's enough to prove it for this. And we first invert this vacuum, we really just get this vacuum, but spread on the entire space, this X, everywhere it's really just a vacuum. And then we do this BRST. So, and you may wonder what's the result of this BRST, and I will tell you what's it. So you consider this stack, so the classified stack of this arc group, and consider the structure global section of it, whatever this means. So and you just make it a fraction algebra inside this D1 and view itself as a fraction module. So this is what you get. And let me explain why this is true. So in other words, I need to justify this formula. Doing semi-infinite cohomology for this band, you really get this O of that thing, which the other way to write it is to get this thing. So the idea is like this back is induced from tree, and this BRST is doing a homology for the neuron part and then doing cohomology for the arc part. So you first induce from arc to neuron and do homology. So these two things, so they actually cancel each other. So therefore, you are really doing cohomology for arc for trivial representation. That's why this is true, and this is indeed O of B L plus N. So that's that calculation, and now we do this integration, and the result we know it. It's denoted by as factorial cohomology on this X of this factorial algebra. So let me give a name for it. Then let's call it omega n. But you view omega n as a module for itself, and you do this factorial homology. So this is what we get. And now this arc. And the other arc is much easier. So you start from vacuum, you do localization, you get just sheaf of differential operators. And the drum cohomology of sheaf of differential operators would be just be the global section of O of bar n. So therefore, so the content of cell 4 is equivalent to the following thing. So I will raise this advanced theorem 4 prime, which really tells you what's the global section of bar n, or global section of structure sheaf. It says O of bar n is the same thing as factorial homology for omega n. It's a module for itself. So, but we know this is really the unit for itself, doing factorial homology for itself. You can just do factorial homology for the algebra. So what we really need is this formula. So it's some very concrete calculation And now, no formal thing can help us. We have to prove this. And then we write both sides in terms of some mapping spaces. So what's this span N? So this span N is like the normal mapping space from X to this Bn. So, or if you want, if you Bn as something defined over X, and we want a section from X to this product. And what's this B of L plus N? So L plus N classify automorphisms of trivial bundles on the disk. So therefore, this really maps on X from disk to Bn times X. So
Just omega and small.
N is what?
What is omega inside the factorization?
It's that's a notation. It means this. So okay, let me get rid of this notation and just write O of B. So now let's look at the statement of this term 4. So it says we have this local thing. So its structure shift produce some function algebra. We do function homology. Homology will get the structure shift of some global thing. And we have seen that before. So namely, in Nick's talk, so he told us the following is true. Oh, sorry, one more minute. So he told us if you consider, for instance, if you consider an alpha D scheme, which is y mapping to x, is some alpha D scheme. He told us that we can consider the horizontal section from x to this y. So this is some globally defined thing. You consider O of this. This is equal to factorial homology of the following factorial algebra. So you consider just the horizontal arcs of this y as defined in Kevin's talk, and you consider the structure shift of this thing, so which is a function algebra, and you do function homology of that. So Nick explained local to global principle tells you that these two things are the same as long as this y is alpha over x.
So you okay.
Yes. So now what are we doing? So we are in trouble in two reasons. So first, so a y is not just Pn times x, because here we are doing just arcs and sections, not horizontal thing. So instead, so what a y now is the V restriction of this Pn times x along the map x mapping to x to the right. So let's ignore this point. It's not so important. So the other thing is we can only apply this to alpha in schemes, but Bn is not alpha. But Bn is as good as alpha. In the following sense, it's alpha in the derived world because Q of Bn is equivalent to O of Bn mod. So here, O of Bn is not a connective algebra. So therefore, you cannot form spec of that in the usual sense. So it's it goes to the right. But you can imagine if you work with unbounded complexes and digit algebra for them, so you can invent some version of spec. And in that sense, this Bn behaves like alpha thing. And this is exactly the case. So then let's call it as good as alpha. And because it's as good as alpha, so you can use Nick's method to prove the general result, which tells you that all horizontal sections, global horizontal sections is factorial homology for all horizontal arcs, which exactly tells you that all upon N is this factorial homology. This is the content of theorem 4. Any questions?
Yeah, it's a prayer. You said earlier for no closing group, every representation, they can filter it through the representation.
Yes.
What's the relationship between that and this fancy sounding thing you just said?
Of course, they are related, you know that. So let me just answer this by saying another feature of this Newton group, which is this ISO only holds for Newton group. So because if you expect something like this to happen, so you want to say the Leffler joint to global section, which is the trivial representation generated category, which is exactly why we can do that before.
So, to make this means remark that you haven't even told us the answer for step 2.
Yes.
But you don't need to, because the next talk does code values suffices.
Yes.
So we can just.
So then let me say it just in minutes, maybe even 1 minute. So we want to understand this function. So just imagine this is just refugee check run. And everything on this picture is acted by refugee check run. So like here, so we are some Sataki, and here we are some Sataki, here with Sataki and Fake, and here everything lives over this BG check. Everything is acted by refugee check run. And to describe a functor from some KL, some refugee check run linear functor from KL to refugee check run, so it's enough to compose with the fiber functor, which is forget functor to that.
No, don't forget one thing, valuation.
Yeah, sorry.
Invariance.
Invariance function. Yes. So this is some game of duality. However, what I said is actually a lie, because in reality there are two different refugee check run action. So recall refugee check run act on this thing by this convolution tensor product introduced by Dennis. But on these things we are using some pointwise tensor product. They are different. But there's something called run magic. Tells you that in this story you can ignore that, because so there's something there's some full subcategory of this refugee check run such that these two monodal structure they coincide. Sorry, not a full subcategory. There's some category mapping to refugee check run such that these two structure coincide. And just restricting to that part, so everything works, and you can deduce the general case from the vacuum case. So that's how to deduce step 2 from step 1.